Hello and welcome to the section on Boolean classification. So we've already seen the core idea. We have a target variable which is categorical, which we embed as representatives in Euclidean space. And in the Boolean classification case, we will embed them in a one-dimensional Euclidean space, the reals, as plus or minus 1. So true might embed to plus 1 and false to minus 1. And then we use regularized empirical risk minimization to fit with various loss function and regularizers. And then we use the Neyman-Pearson metric with our choice of kappa to express our preference for false negative and false positives. And we can validate using that as our performance metric. And of course, when kappa is 1, this reduces to the sum of the false negative rate and the false positive rate, which is the error rate. Now I want to look now in more detail at possible loss functions that one uses for Boolean classification. Now here y can only take values minus 1 or 1. And so really there are only two scalar loss functions. So normally when we think about a loss function, we have a function which is a function of y and y hat, and the loss function is going to be small or 0 when y is equal to y hat, so along this line, and it's going to be increasing as we move away from that line. But in our case, y only takes two values, and so there's y equal to 1 and y equal to minus 1. And so I've got a function which in theory is a function of the entire plane, the loss function, L of y and y hat and y, but really it just takes two possible values for y. And so I really only evaluate the function along this line and along that line. And along that line the function is L of y hat 1, and along this line it's L of y hat minus 1. Now, we might call them something else. We might call this equal to LA of y hat, and this LB of y hat, just to be explicit that even though we write them with two arguments, they really are both functions on one-dimensional space, the space of y hats. And when we look at what this function LA or L y hat is, it tells us how much y hat irritates us when y is 1. And the other one, LB, tells us how much y hat irritates us when y is minus 1. And we would look for this function here to be small at y hat is 1 and increasing away. And similarly, this function should be small at y hat is minus 1 and increasing away. And that sounds reasonable based on our intuition for loss functions in two variables, but actually that's not quite what we want for Boolean classification. And the reason is that if y is 1, then we would like a y hat that unembeds to give us 1 also. And that means that any y hat which is positive should give us a low loss. And similarly, when y is minus 1, we'd like a y hat that unembeds to minus 1. And so any y hat that's negative should give us a small loss. And so what we really want is we want this LA function over here, we want it to be small when y hat is positive. We want it to be small here and growing in this direction. And we would like this function to be small here and growing in that direction. And so we've got to look at two functions that kind of behave in the opposite way. L of y hat 1, we'd like to be large when y hat is positive, is when y hat is negative, and small when y hat is positive. L of y hat minus 1, we'd like to be small when y hat is negative, and large when y hat is positive. The way we're going to get this is we're going to define a penalty function, p, and we'll have L of y hat minus 1 be just p of y hat, and we'll have L of y hat 1 be p of minus y hat. Now, in order to get the property that false positives and false negatives irritate us different amounts, we're going to scale one of those. So in fact, we'll have L of y hat 1 be p of y hat, and L of y hat 1 be kappa times p of minus y hat. Now let's look at our favorite loss to date, the square loss function. Now, if we had a loss function which was 1 whenever we chose the wrong answer, and 0 whenever we chose the right answer, well, that would be this loss function right here. And the square loss function is this purple blue curve here. That's for the case when y is minus 1. Here I've scaled on the right hand side everything by kappa. So here kappa is 2. And so I've got a loss function which is 2 when I've got an ideal loss function which is 2 when y hat is negative, and 0 when y hat is positive. And I've got the square loss function. Here. And, well, it does satisfy some properties that we like. In particular, when y is minus 1, the loss is large when y hat is positive. Over here. Use a different color. There. And similarly, when y is 1, the loss is large when y hat is negative, which is what it should be. And then we have the part where the square loss lets us down. The square loss also becomes large over here, where it should, in fact, be small, where we'd like a loss to be small, because any y hat which is negative should earn us a small loss when the true y is minus 1. Because any y hat that's negative is going to unembed to a y hat value of minus 1, which is exactly y. And the same over here. When y is 1, the square loss grows again, and that's not the property that we want. On the plus side, of course, the resulting ERM problem is a least squares problem, and so it's easy to solve. Now, there's another loss function that we might consider, and that's the Neyman-Pearson loss. And here it is. This is our ideal loss function. So this is the loss function which is 1 when y hat is going to embed to the wrong value, and 0 when y hat is going to embed to the right value. And we scale that by kappa when y is 1. And as a result, the Neyman-Pearson loss is the loss such that when we evaluate the empirical risk, well, what's going to happen? We're going to score 1 point for every time y is minus 1 and y hat is 1. And we're going to score kappa points every time y is 1 and y hat is minus 1. And so it will equal to kappa times the false negative rate plus the false positive rate, which is exactly the Neyman-Pearson performance metric that we defined before. And so this is the ideal loss function. For any particular kappa, use this as the loss function and do empirical risk minimization with this loss function. And the empirical risk will be exactly our desired performance metric. That's a good thing, but the unfortunate thing is that it's actually very hard to minimize empirical risk with the Neyman-Pearson loss. And the reason for that is twofold. One is that it has discontinuities at the origin. And those discontinuities make many algorithms for solving empirical risk minimization not work well. The other is that the derivative is 0 everywhere else. And that's another feature that makes empirical risk minimization algorithms not work well. If the derivative is 0, then if we've got a particular predictor and we change its parameters slightly, then what's going to happen is that the value of the empirical risk is probably not going to change, because we're going to move our resulting y hats, say, from here to here, and in both cases we're going to earn exactly the same empirical risk. And so it's hard to have an algorithm which is based upon small changes to theta and searching over small changes for theta. It's hard to have such an algorithm work when one has a loss function which has 0 derivatives everywhere. Instead we don't use the Neyman-Pearson loss. And in fact we get better performance if we use different loss functions. And those different loss functions not only give us better performance, but are actually also easier to minimize. If the loss functions are convex, well, we've already discussed how convex optimization problems are simpler to solve than problems where the objective function isn't convex. And of course we need the regularizer to be convex too. Well, then there's a very efficient solution. But even if the loss function isn't convex, it's still very useful in practice and very commonly used. So here's a loss. This is a function called the sigmoid function. This is 1 on 1 plus e to the minus y hat. That's this function right here. And this function is, of course, the flip of it. So we've replaced y hat by minus y hat and scaled it by kappa. And you can see that this is a nice, smooth approximation of the Neyman-Pearson loss. We've smoothed it out, and that's dealt with both of our problems. It's removed the discontinuity, and it's removed the 0 derivative problem. So this is a nice differentiable approximation of the Neyman Pearson loss. It's not convex, but nonetheless it can work well. Here is one of the most commonly used loss functions for Boolean classification. This is the logistic loss function. This is the log of 1 plus e to the y hat for the case when y is minus 1. And in the case when y is 1, we flip it and we scale by kappa. And you can see that, well, it's not the perfect approximation to Neyman Pearson, but it does grow in the right direction. It's small on the left-hand side, and it grows as we move to the right. And the thing it doesn't do is it doesn't flatten out. Instead, it keeps on growing. Whereas there's no reason in terms of a performance metric to penalize a y hat which is very large over one that's not very large. As long as it's greater than 0, it will unembed to 1 no matter what. But this is convex as a result of it not flattening out, and so it's both differentiable and convex. And this is very commonly used and works very well in practice. The other very commonly used loss function for Boolean classification is the Hinge loss. And this is the positive part of 1 plus y hat when y is minus 1, and again the flip and scale when y is minus 1. And so it's a function which is 0 when y hat is less than minus 1, and then increases linearly. This is convex. It's differentiable almost everywhere except at this one point right here. This is very, very commonly used as well. This is the other most common choice for Boolean classification. And we might make up our own loss function. So here's one. Here's one we made up, which we've called the hubristic loss, which is a cross between the Huber and the logistic. So it behaves, it is constant and 0 when y hat is less than minus 1. It grows like a quadratic here to approximate that change in value from 0 to 1. And then it continues growing linearly at the same rate in order to have a smooth derivative at the origin. Now, several of these classifiers are extremely popular. If we're using the square loss and the square regularizer, that would be called a least squares classifier. If we use the logistic loss and any regularizer, then that's called logistic regression. And so that would be called, for example, logistic regression with an L1 regularizer. If we use the hinge loss with the square regularizer, that has the rather bizarre name of the support vector machine. And what that means is it's regularized empirical risk minimization with that particular loss function and that particular regularizer. Here's an example. On the left here we have the classifier that's generated using the logistic loss. There's no test set here and there's no regularization here. We've got a lot of data points, and so there's no real benefit in either of those. And this is just, of course, a toy example. And you can see the logistic loss gives us an error of 16% on this particular data set. On the right here, we see exactly the same data set, only the classifier has been computed with the squared loss. And we can see very similar performance. In fact, the only difference is that this has slightly smaller error rate, 15% as opposed to 16%. But that's in no way a general conclusion, just a particular feature of this data set. In general, one expects quite similar performance between the different losses that one might use for Boolean classification. Sometimes the logistic loss or the hinge loss do better than squared loss. But as usual, the only real way to determine that is through validation. This is the support vector machine. This is the hinge loss combined with the square regularizer. And it has a peculiar feature that is worth observing. And it only happens in this somewhat artificial case, and so it never really happens in practice, but it is worth at least discussing here. And that is that if you have a data set where the two classes are perfectly separable. So here we have a data set where all of the blue points are up here and all of the red points are down here. And so our classifier, our predictor, is doing perfectly. It's getting 0 training risk. And but it has an additional feature, and that is that that's this line and this line. And those lines are the lines in X space where theta transpose X is plus or minus 1. So theta transpose X is 1, maybe here, and theta transpose X is minus 1, maybe here. Or they may be the other way around, depending on which points are 1 and which points are minus 1. Now, why should that be the case? Now, the reason that's the case is as follows, is that the theta transpose X is 1 line is perpendicular to the direction that theta points in. So theta here is a vector and it points in this direction, in which case that's theta transpose X is 1 right there. Now, what happens if I make theta larger? Well, that means that theta transpose X is 1 is going to move in a bit, and similarly theta transpose X is minus 1 is also going to move in a bit towards the origin. And now if I evaluate the predictor at my data points, well, the predictors at the data points gives me y hat, and y hat is theta transpose X. So all of these points have a theta transpose X value, have a y hat value, which is greater than 1. And all of these points have a y hat value which is less than minus 1. And so, because if I look at this loss function here, right, all of the blue points which have a y hat value of greater than 1 are going to give me 0 in my loss. And then if I look at this plot here for the loss for the red points, all of my red data points have a y hat value of less than minus 1, and so they're also going to give me 0 loss. And so as long as theta is sufficiently large and pointing vaguely in this direction, I will end up with exactly 0 empirical risk. Now, what's happening is that here we've got the square regularizer. And so that's a penalty on the size of theta. And so by minimizing the empirical risk plus lambda times the norm of theta, we're going to try and make theta small. And so the best that can happen is that we make theta sufficiently, well, so depending on the value of lambda, right? For some values of lambda, we will find that the right thing to do is to make theta as small as we can, but still keep the loss, the total loss, 0. And that's exactly what's happened here, is that when we make theta small, the smallest we can make theta and yet have a loss of 0 is when the theta transpose x is one line has moved up, right the way up against this one data point right there. It's a blue data point. And the corresponding theta transpose x is minus one line has moved up against these data points which are right here on the boundary. And so the theta vector, it is a normal vector to the boundary between the two classes, and its magnitude is equal to 1 over half the margin. So that's the margin half width, and that distance is equal to 1 over the norm of theta. Again, this is a very peculiar special case that you never see in practice because you don't have interesting problems where the classes perfectly separate. Let's look now at a more practical example. This example is the Australian weather, where what we have is we have data collected at many different weather stations across Australia, and at each of those weather stations we've collected attributes of the weather such as temperature, pressure, humidity, wind, and so on. And this data was collected over 10 years from 2007 through 2017 and consists of 142,000 or so records. And the objective we have today is that given this data, predict whether or not it will rain tomorrow. And so included in this data is rainfall, and the target variable is whether or not it rained the next day. Now, if we look at all of these data records, it turns out there are quite a few missing entries in the data. And so what we've done is we've gone through each of the records of the data, and any record that has any field missing at all has been removed. And so once one does that, one only ends up with 112,000 or so records, which is still a substantial amount of data. We will see later in the class how to fill in missing values in the data set, but for now we've just removed them. And this data, of course, we didn't collect it ourselves. This data is from Kaggle. There's a link here, and you can go there and get the data yourself and play with it. Now the fields in the data in each record, there's a bunch of numeric fields. Those are here listed. Now the way this data is collected is that it's daily data, and so at each of the different sites, there are 44 different sites. There's a record collected each day, and that measures attributes of the day's weather at that site. So, for example, the minimum temperature and the maximum temperature, or the minimum temperature and the maximum temperature over that day. And a day starts at 9 a.m. and ends at 9 a.m. Similarly, we have rainfall, which is total rainfall over the day, the wind gust speed, the wind speed at 9 a.m., the wind speed at 3 p.m., the humidity at 9 a.m. and the humidity at 3 p.m., the pressure at 9 a.m. and the pressure at 3 p.m., the temperature at 9 a.m. and the temperature at 3 p.m. These are all numeric fields, of course they're all in different units, and we will embed them and standardize them. We also have categorical fields. We have the location. As I said, there are 44 possible locations. Each of the wind speeds has an associated wind direction, and those are the 16 compass points, things like east, southeast, and we also have a field which is whether or not it rained today at that location, which is either yes or no. And then there's one more final field in the data, and that is the date on which the record was taken. So let's take a look at some of this data. Because there are over 100,000 records, we're only looking at a small 2% random sample of the data just to get a feel for it. And just looking at a couple of the features here. So here we have the minimum temperature plotted on this axis and the maximum temperature plotted on this axis. And we've plotted in blue those points for which there was rain the next day, and red those points in which there was no rain the next day. And you can see that there is some indication here. Over here, over here, we're getting much more chance of rain the next day than over here. And so the data does indicate that, although by no means is there a clear separation. Now over here we've looked at the 3 p.m. temperature and the 3 p.m. pressure, and we can see again that when both of those are small, there's a chance of rain tomorrow. When both of those are large, there's much less chance of rain tomorrow. Now, where we embedded the data, well, we have 12 numerical fields, and those are just embedded as they are via the identity map. Each one of those wind speeds is associated with a wind direction, which we embed as one hot. Whether or not there's rain today, that's simply a Boolean categorical, so we embed it as -1 or 1. It turns out that the date and the location fields actually did not improve the performance after validation, and so we simply removed those. We standardized, we add the constant feature. How does this work out? Well, there are 12 numerical fields. There are 3 times 16 1 hots, and so that's 48 plus 12, that's 60, and then there's rain today, so that's 61, and then there's the constant feature, and that gives us 62 dimensional x. The target variable is y, which is simply a Boolean categorical, whether it rains tomorrow or not, and that's simply embedded as -1 or 1. Now here we're going to use the logistic loss, which we've seen before. When y is -1, the loss at y hat is log 1 plus e to the y hat. And similarly, when y is 1, it's kappa times log 1 plus e to the -y hat. And we use a linear predictor, and we use square regularization. Now we randomly split into an 80-20 training and test sets. It turns out when you do this that the training error and the test error are, so the training empirical risk and the test empirical risk are extremely close. And as a result, one only needs a very small amount of regularization, and there's no point sweeping over regularization because there's no dip in the test loss to be gained. And so as it does, we just fix the regularization amount to a very small fixed amount, something like 10 to the -5 for lambda. And so here we've plotted the operating characteristic, the ROC curve, and you can see that there's a red curve and a blue curve, and both of them are pretty much on top of each other. The minimum probability of error point on the ROC curve is right about here. That's the minimum probability of error classifier, and it achieves a false negative rate of about 0.08 and a false positive rate of about 0.08, so a total probability of error of about 16%, which is pretty good. It's worth comparing also with this point down here. That's a classifier which achieves an error rate of 22%. And the way it does that is by always predicting that it will not rain tomorrow. And that's because the data itself contains about 22% days with rainfall, and the remaining 78% of days have no rain. And so this is a very simple predictor, which is doing reasonably well with a prediction with an error rate of 22%. Of course, it's very trivial, and that's really the baseline which we have to do better, which we have to improve upon. And so we're achieving 16%, which is a significant improvement over 22%. It would be nice to do better than that, but with the linear predictor that we're using, this seems to be the best achievable. Now, if we look at the minimum error predictor, and we look at its parameter vector theta, and then we can plot here the components of theta, theta I against I. This says absolute value of theta I. It's not, of course, the absolute value, it's just theta I. What we see is some large values and some small values. These large values here don't matter because there are 16 of them, and those 16 entries of x are the one hot embedded values for wind near at 9 a.m. And because those columns are one hot embedded, they sum up to 1. And so this is just equivalent to a constant term in the predictor. And that's just the way the training worked out. We could simply subtract off this term and add it to the theta 1 term, and it would give us an equivalent predictor. So those aren't the significant thing. Some interesting things are important. This and this. This is the pressure at 3 p.m. and this is the pressure at 9 a.m. And so we've got a predictor here that depends very strongly on the difference between the pressure at 9 a.m. and the pressure at 3 p.m. And so if the pressure is falling, so 3 p.m. pressure is much less than 9 a.m. pressure, then that is a strong predictor of rainfall. And of course, this is a very well-known phenomenon in the weather, that rapidly falling pressure indicates that a storm is coming. The other features here that are significant are, this is of course just the constant term, so it's not really a feature. This one right here is the wind gust speed. This one here is humidity at 3 p.m. And these two are min temp and max temp. Since those are the significant features, we can simply say let's retrain our predictor using only those 6 features: the min temp, the max temp, the wind gust speed, humidity at 3 p.m., pressure at 9 a.m., and pressure at 3 p.m. And if you do that, then you end up with a classifier that achieves a probability of error on the test set of about 16.5%, which is basically the same as the classifier we had with all of these features. And so the rest of these features are irrelevant at predicting rainfall. at least with the current linear predictor. So it's possible that one could do better, maybe by using a more complicated predictor such as a neural network predictor, maybe by using some more sophisticated feature engineering, combining features. And this is simply, of course, a first foray into designing a predictor to predict rainfall. Okay, so next section we will talk about classification where there are more than two classes, multi-class classification, and we will see the appropriate form of losses to use in that case.